Most of us grew up hearing the same simple story. Oil comes from dinosaurs. But that explanation starts to fall apart the moment you think about the scale. Even if every dinosaur that ever lived had somehow been turned completely into oil, it still would not come close to explaining the amount of oil the world has actually found. Because the total biomass of all dinosaurs combined was tiny compared with something else that existed in unimaginable quantities, the accumulated remains of microscopic plankton building up over immense stretches of time. And that is where the real mystery begins. So, where do people think oil actually comes from? For some, the answer is simple. In parts of the Middle East, especially in deeply religious communities, oil is often seen as a gift from Allah, a resource placed beneath the ground by divine will, a blessing that shaped the fate of entire nations. Science tries to answer that same question in a very different way, and for more than a century, that debate has mostly centered on two competing ideas. The first is the mainstream scientific view, and it begins not with dinosaurs, but with microscopic life. Back in the 1800s, geologists noticed a pattern that kept repeating. Oil was consistently found in rocks that had once formed beneath ancient seas. Over time, that led scientists to a powerful conclusion. Oil came from vast quantities of tiny marine organisms, plankton, algae, and bacteria that lived in shallow oceans hundreds of millions of years ago. These organisms were so small that millions of them could exist in a single drop of seawater, but over immense stretches of time, they lived, died, and settled onto the seafloor in such staggering quantities that the total organic mass they left behind far exceeded anything all the dinosaurs that ever lived could have contributed. But that is only one explanation. In the 1950s, Soviet geologist Nikolai Kudryavtsev proposed a very different idea. He argued that oil might not come from ancient life at all. Instead, he suggested that hydrocarbons could form deep inside the Earth under extreme heat and pressure, then slowly rise through fractures in the crust. Later, astrophysicist Thomas Gold helped push a similar argument even further, suggesting that at least some oil might have a deep, non-biological origin. This became known as the Abiogenic Theory, the idea that oil can form without life. And that raises the real question. If oil can form deep inside the Earth without any help from ancient oceans or dead organisms, can that process actually explain the giant oil fields the modern world depends on today? Before we decide which theory explains oil best, it helps to look at who actually won the geological jackpot. The single biggest winner on paper is Venezuela. It holds the world's largest proven crude reserves, with more than 300 billion barrels, much of it concentrated in the Orinoco Belt. But if you zoom out from one country to an entire region, the real heavyweight is the Arabian Peninsula. Saudi Arabia, Iraq, Iran, Kuwait, the United Arab Emirates, and Qatar together hold an enormous share of the world's conventional oil. Russia, Canada, the United States, and the North Sea all matter too, of course. But the global map is still strikingly uneven. And when geologists rewind the clock, that imbalance starts to look a lot less random. Large parts of what are now the Gulf states, along with neighboring parts of the Arabian Peninsula, once lay beneath warm, shallow seas, connected to the ancient Tethys Ocean. Northern South America, especially Venezuela, also developed vast sedimentary basins tied to marine and deltaic environments. In other words, some of today's richest oil regions were once exactly the kind of places where huge amounts of organic material could build up. But that raises the real question. If ancient seas existed in many parts of the world, why did not all of them become oil kingdoms? Part of the answer is that ancient geography did not stay where it was. Earth's crust is broken into moving plates, and over millions of years, those plates split apart, collided, sank, and folded over each other. Oceans opened and closed. Seafloors were buried, lifted, warped, and in some cases pushed up into dry land. That is why a place that is now desert could once have sat beneath a tropical sea. But plate tectonics only set the stage. The real difference came down to preservation, burial, heat, and timing. It began with trillions of microscopic plankton, algae, and bacteria living in those ancient waters. When they died, they drifted down to the seafloor. In some basins, especially in parts of the ancient seas covering what is now Saudi Arabia, Iraq, and Iran, the bottom waters contained so little oxygen that much of that organic material did not fully decay. It stayed preserved. Then mud, sand, and more sediment kept piling on top. Over millions of years, kilometers of rock built up above it, and as that buried material sank deeper into the crust, temperatures rose. At the right depth, it entered the oil window, where heat and pressure transformed that preserved organic matter first into kerogen and then into liquid oil and natural gas. And even then, forming the oil was only half the battle. Freshly generated oil is lighter than the salty water already trapped in the rock, so it starts moving upward through tiny pores and fractures. Most of it would have kept rising until it escaped, unless geology stopped it. That only happened when two things came together: a trap, usually an upward folded rock layer acting like a natural dome, and a seal above it made of shale, salt, or clay that the oil could not pass through. Only then could oil accumulate instead of disappearing. That is why not every ancient sea became an oil giant. Marine life alone was not enough. A basin also needed the right preservation, the right burial, the right heat, the right migration path, and the right trap. Only a few places got the full sequence. And even when all of that works, the story is still not over, because oil is not just oil. The same basic process can still produce very different kinds of crude, because what matters is not just how the oil formed, but what happened to it afterward. In Saudi Arabia, much of the crude remained relatively mobile after formation. In Venezuela's Orinoco belt, much of it sat in cooler, shallower conditions where underground microbes gradually consumed the lighter hydrocarbons, leaving behind extra heavy crude with more sulfur and a tar-like consistency. And those differences matter. They shape prices, refining costs, infrastructure, and ultimately geopolitics. But that brings us back to the deeper mystery. If oil fields can end up so different even when they form through the same general process, could at least some oil have come from somewhere else entirely? That is where the story turns to the Abiogenic Theory. At the beginning of this video, we mentioned a very different possibility: the Abiogenic Theory, the idea that at least some oil may have originated deep inside the Earth rather than from ancient life. If that were true, we would expect giant oil fields almost everywhere, even in hard crystalline rocks far from ancient seas. But that is not what we see. Almost all major oil fields are concentrated in sedimentary basins filled with organic rich rocks formed in ancient marine environments. In other words, they appear exactly where we would expect them to be if oil came from buried life. That prediction was even tested in the real world. If oil were really just a deep mineral resource that could rise almost anywhere, then you should be able to strike meaningful oil even in hard crystalline rock. In 1980, Thomas Gold backed drilling deep into granite in Sweden to test exactly that idea. The result was a reality check. They found almost nothing aside from small amounts of lubricating oil traced back to the drilling machinery itself. And the evidence does not stop there. Inside crude oil, scientists find biomarkers, chemical fossils such as steranes and hopanes. These are molecular leftovers from ancient algae, plankton, and bacteria. Their structures match compounds made by living things, and no known deep earth process can create them in the same way. The carbon in oil tells the same story. Living organisms strongly prefer carbon-12 over carbon-13, and oil carries that same signature. So when you put the clues together, the rock layers, the biomarkers, the carbon isotopes, they all point in the same direction. The vast majority of the world's oil came from ancient microscopic life, buried and transformed over millions of years. That leads to the next question. If hydrocarbons can still form naturally today, does that mean oil is renewable? Technically, tiny amounts of hydrocarbons can form through natural chemical reactions without life. Scientists have observed this in places like deep-sea hydrothermal systems. But that does not make oil renewable in any meaningful human sense. The giant oil fields that power the modern world required extraordinary amounts of organic matter, accumulating over hundreds of millions of years, then passing through the right burial, heating, migration. and trapping conditions. That process is unimaginably slow compared with how fast we burn through oil today. So yes, nature may still be making tiny amounts. But no, it is not making them fast enough or in large enough quantities to replace what modern civilization consumes. On human timescales, oil is effectively non-renewable. So the real story of oil is both stranger and less comforting than the myth. It came from microscopic life in ancient seas, and on human timescales, it is effectively finite. If this changed the way you think about oil, let me know in the comments what surprised you most. And if you enjoy these kinds of deep dives, subscribe to Simple But Surprising for more.